Right now, somewhere in this building, steel is burning at 2000 degrees Fahrenheit. It's 4 in the morning. Most of the world is asleep. But inside this forge, the work never stops. It hasn't stopped in 40 years. This is one of the most extreme manufacturing environments on the planet. The temperatures in here will hit numbers that your kitchen oven cannot reach in a lifetime. The machines shake the ground when they work. The air itself glows orange. And the men and women who work inside it, they walk through this every single day. One switch, and 400 tons of industrial machinery begins to breathe. The forge is awake. And what happens here next, most people will never see in their entire lifetime. Stay with us. It all starts here. Raw steel bars, each one weighing over 300 kilograms. The alloy inside them was engineered specifically for this purpose: high carbon, high manganese, designed to absorb forces that would destroy ordinary steel. But right now they are just bars. Cold, inert, waiting. Step 1. Cut these bars into exact length slugs. For that, you need a blade that doesn't care that the bar in front of it is 80 millimeters of hardened steel. Watch what happens when 500 tons of hydraulic force meets a steel bar. That shower of sparks is not decoration. That is friction energy so intense it briefly heats the cut surface to over 1000 degrees in under a second. Every slug that comes off this machine is measured, not approximately, exactly, because at 2000 degrees, a 2 millimeter error becomes a rejected chain. And a rejected chain means wasted days of work and thousands of dollars. These workers are not just checking numbers. They are the last line of quality before fire. The furnace. This is where everything changes. Those cold gray slugs going in the door right now, they are about to experience a molecular transformation. The carbon atoms inside the steel are going to rearrange. The crystal structure is going to rebuild itself into a new formation, one that makes the metal soft enough to shape, without losing any of its eventual strength. The temperature in there is 1200 degrees Celsius. That is more than twice the temperature at which aluminum melts. And the steel will come out the other side, glowing white. The pyrometer reading is not a suggestion. Exactly 1180 degrees. Not 1150. Not 1200. Exactly 1180. At that precise temperature, and only at that temperature, the steel has the exact plasticity it needs to be shaped without cracking. This is why the forge operates by the numbers. Because at this scale, intuition is not enough. This is the bending press. It weighs 80 tons. It can apply 600 tons of forming force. And it has approximately 4 seconds to shape this slug before the steel cools past its working temperature. There is no second attempt. Watch the ram come down. See the black scale shattering off the surface as the steel bends? That is the iron oxide crust breaking apart under deformation. Underneath it, the steel is flowing, slowly, heavily, guided by physics that engineers calculated to 5 decimal places. And in under 4 seconds, a flat steel slug has become a perfect U-shape. The robotic systems never get tired. They never hesitate. But the operators, they are watching things no sensor can read. The color of the steel, the sound of the press, the subtle signs that tell an experienced worker whether the temperature was exactly right or just close enough. Now comes the moment where individual components become something greater. Each U-link must be threaded through the previous finished link, precisely, while still warm, and then closed. This is where the chain is actually born. Not in the furnace. Not on the press. Right here, in this human act of threading one piece of steel through another. Chain makers have done this exact motion for 200 years. The machines around them changed. The act itself never did. And now, the most critical 0.3 seconds in the entire manufacturing process. The weld. Those copper electrodes carry more electrical current than a medium-sized city block at peak power. When they close on that link seam, everything that happens next happens faster than you can blink. Step back. That light is not safe to look at without protection. That is a sustained electrical arc at 20,000 amperes. Driving enough concentrated heat into a 3mm steel seemed to melt both faces simultaneously and turn them into a single pool of liquid metal. For 0.3 seconds, that link does not have a seam anymore. It has liquid steel where the seam used to be. The upset squeeze, that final hydraulic press at the exact moment of welding, this is what makes flash but welding superior to every other joining method at this scale. The liquid metal is squeezed under enormous pressure. The crystal structures of both faces fuse together at a molecular level. The engineers call it a forged weld. The result, that joint, right there, is actually stronger than the original steel bar it came from. Not as strong. Stronger. But strong is not the same as finished. The flash ring must come off. First the trimmer, then the robot, then, by hand, the final pass. That bare thumb running over the weld seam is the final quality check that no machine performs. Decades of experience in the skin of one hand, reading smoothness that gauges cannot measure. No ridge, no weakness, just one continuous piece of steel, from what started as two separate ends. Induction hardening, the final thermal treatment. The chain passes through a coil that generates a rapidly alternating electromagnetic field. Eddy currents form inside the steel links themselves, heating the outer layer to critical temperature in under 10 seconds without touching the surface. Watch the links transform as they pass through the coil. Cold gray to glowing orange in seconds. And then, the quench tank is waiting. When 1100 degrees steel hits quench oil at that velocity, the oil surface ignites. That is not a malfunction. That is designed. The flash fire lasts less than 2 seconds. What matters is what is happening beneath the oil surface. The steel is cooling from 1100 degrees to below 200 degrees in under 8 seconds. That rapid thermal shock traps the hardened crystal structure inside the steel, locking in a hardness that the metal cannot achieve by any other method. What comes out of that tank is a different material from what went in. But no chain leaves this factory on the strength of process alone. Every batch, every time, the tensile test machine is going to pull this chain apart. Or try to. 100 tons of force, 200 tons, 350 tons. The needle does not lie. At 400 tons, the steel is talking. You can see the micro-deformation on the surface. The link is elongating by fractions of millimeters under forces that would crush a car in a single second. And it holds. That stamp into the steel is not ceremonial. It is a promise to every ship captain, every crane operator, every construction worker who will depend on this chain, that what they are holding has been tested to destruction and refused to break. Shot blasting, galvanizing, final protective coating. This chain began as a rough steel bar stacked in an outdoor yard. It has been through fire at 2000 degrees, 20,000 amperes of electrical current, 600 tons of forming force, and a molecular level thermal treatment. What remains is a product engineered to perform for decades in the most demanding environments on Earth: deep ocean, Arctic weather, construction sites, and industrial lifting systems that never rest. One link, forged, welded, tested, finished. Somewhere right now, a chain exactly like this one is holding a 100,000-ton ship steady in a storm, lifting the steel skeleton of a building 50 floors up, moving the mining equipment that extracts the materials to build your world. And it started, right here, as a cold steel bar in a yard, at 4 in the morning, when the rest of the world was asleep. This is what industrial manufacturing looks like when no shortcuts are taken. This is how the world is held together.